Hi, everybody. Um, yeah, so I want to talk about this recent project that's about achieving a high throughput Byzantine consensus on networks with a lot of bandwidth variability. I'm a networking researcher, not really a consensus person. So when we started looking at this problem, I was interested in understanding how do these protocols actually work on real world networks. And that was kind of the original motivation for this, for this project. This is joint work with my PhD student, Lei Yang, who's in the audience, Seojin Park, who's a former postdoc at MIT, soon to be a professor at USC, Siram Khannan from UW, and David Shea at Stanford. So to set the stage for this, many blockchains need to deploy consensus protocols at internet scale across different networks around the globe. These networks can exhibit significant variability in bandwidth, both across nodes and across time. So on any given day, say a node on the East Coast in the United States may be faster than a node in Southeast Asia. And these network speeds can actually change over time, depending on time of day, depending on a lot of factors like traffic conditions in that network at that point in time, and so on. And it turns out, as I'll describe, existing BFT protocols actually leave a lot of performance on the table when faced with this kind of bandwidth variability. So to understand what the issue is, let me kind of quickly talk about the basic structure, in an abstract sense of BFT protocols. BFT protocols, as you all know, run in epochs. In every epoch, they append a batch of transactions or a block of transactions atomically to a log or a ledger. And every epoch has two main phases. There's a broadcast phase and there's an agreement phase. In the broadcast phase, some node proposes a block of transactions, and typically all the other nodes will download it. Once they've downloaded it, they will exchange votes to come to agreement and decide whether they're going to append this block to their logs. And this typically requires 2/3 of the nodes. Let's say for F is 1/3 of N, requires about 2/3 of the nodes to actually vote. And at that point, the nodes agree to append the block. They will then move on to the next epoch. So that's kind of the basic structure of almost any BFT protocol. Now, the issue here is that agreement requires 2/3 of the nodes to vote, and therefore 2/3 of the nodes to have actually downloaded the block before they can vote. And in networks with a lot of variability, this creates essentially stragglers. So if I have a bunch of slow nodes, they're going to take a long time to download the block. And in every epoch, you have to wait for that 2/3 final sort of vote before you can make progress. So if you have fast nodes, they can't really use their entire network bandwidth. They have to stall waiting for that final vote. And that 2/3 slowest node becomes the bottleneck for that epoch. So that's kind of the basic issue. The question is, can we get rid of this type of bottleneck? In particular, is there a way to design a consensus protocol that will achieve sort of what the available throughput of the network is, regardless of whether there's bandwidth variations across the nodes? And as I'll describe, what we're really going to try to do to achieve this is we're going to try to take block download off of the critical path of the consensus protocol so that they can actually come to agreement without ever downloading the entire block. So how is this possible? So to reach consensus, obviously the nodes need to order these blocks, but it's kind of not hard to observe that you don't really need to download the blocks necessarily to order them. You could order some other commitment to the block. So for example, a straw man kind of solution is maybe you can order just a hash of the block. So the node that's proposing the block could broadcast the hash instead of the actual block. This is hopefully a lot smaller than the block, so all the nodes, even the slow nodes, can download it quickly. They could then vote, come to agreement that this is the block that they're going to actually be appending to their logs, and then move on to the next epoch. And then uh, later on, every node could go ahead and download the actual block, and at that point execute, the transactions and so on. So this would actually ensure consistency because when I'm once I've kind of agreed to the hash, if I get the block, I can just go ahead and confirm it because I know that all the other nodes will also only accept kind of a block that matches the same hash. So fairly straightforward. But this approach doesn't actually work because the node that sort of proposes the block could be malicious, and it could actually not produce the block when the nodes later go to download it. So at that point, nobody has the block. They've already kind of agreed to this hash, and they can't make progress. So we lose liveness. So this hash is agreeing on kind of an ordering of the hashes is enough to protect consistency, but it doesn't guarantee liveness. It's kind of a basic problem, right? Okay, so what can we do? Well, if we could actually come to agreement that a block of data is available in the network without downloading it. So I'm going to call, this is usually called the data availability property. And really, that's really all we need to actually make progress. So if nodes can basically agree about data availability, they can proceed and then later download, the blocks, and this would ensure that they can each go in and download the block at their own pace. But the key is to only make progress once you know that the block is available, and that's going to be kind of the basic approach that I'm going to talk about. So this leads to kind of this key concept, in this design. In existing protocols, broadcast and agreement are run in lockstep. And if you think about it, that broadcast is actually serving two purposes. It's serving to deliver the data, and it's serving to essentially guarantee the availability of the data. Nodes just know that the data is available by downloading it. But we don't really need to actually deliver the data to continue the sort of make progress in consensus. And we're going to decompose this broadcast into two separate steps, ensuring data availability and then downloading the data. The data availability is necessary, so it's going to be running in lockstep with agreement, but the downloading of the data can essentially be done asynchronously out of band, and doesn't have to be run lockstep with agreement, and that's going to allow the protocol to make faster progress. So the kind of question here is, how do we ensure data availability? Well, there's been actually a bunch of work on this, and actually Christian Cashin and Stefano Tesario introduced this notion of asynchronous verifiable information dispersal that we're going to build on. The idea here is that we can essentially guarantee data availability but using erasure codes. So we can take this block and we can encode it using an erasure code. And the property of the erasure code is that we know that if we're able to retrieve enough encoded chunks, we'll be able to reconstruct the block. So we give each node a chunk from the block, an encoded chunk. And note that the sizes of these chunks are order b over n, where b is the block size and n is the number of nodes in the system. So this can be a lot smaller than actually downloading the entire block. And at this point, nobody has the full block, but we know that if enough of these have been dispersed in the network, we'll be able to download it later and reconstruct the block. So when a node eventually wants to actually download or retrieve the block, they'll contact their peers, collect enough of these encoded chunks, and then decode the block. So that's the basic kind of construction. Now, before kind of just using an off-the-shelf uh, verifiable information dispersal protocol, and by the way, like the protocol that I'm going to talk about is all in the asynchronous network model, and that's why this is an asynchronous VID protocol. Uh, Before just using an off-the-shelf protocol, we noticed that um, it's not just this erasure code. Um, State-of-the-art VID protocols have an additional sort of complexity that's quadratic in the number of in the size of the system. And this is really there because they need to ensure that the encoding that I'm talking about was done correctly. To do that, they include these cross checksums in every message that they're sending as part of the dispersal process, and that gives you a quadratic kind of overhead. And that turns out to be a sort of a problem in practice for the approach that I'm going to talk about. So let me give you an example. Here's an example. Suppose you want to guarantee data availability of a block of size 1 megabytes. And I'm going to show you a couple of different strategies. The simplest would be to just do broadcast. So regardless of the scale of the system, every node has to download 1 megabyte of data. Okay. So here's what you get with a state-of-the-art VID protocol called AVID-FP. And you can see that initially, as you scale up the system, every node has to download less and less data. But eventually, that quadratic term is going to become overwhelming. And here at about 120 nodes with these parameters, you basically get no savings compared to just doing broadcast. So in this project, we've come up with a new VID protocol that actually reduces that quadratic communication overhead to linear overhead. And this allows you to essentially use this VID protocol in the way that I've described for practical block sizes and even at relatively large network scales. So we call this protocol AVID-M. Let me tell you kind of what the main idea is. As I mentioned, the kind of core issue is how to ensure that the encoding was done correctly. If it's done incorrectly, then of course you have a problem, because when people go to retrieve the block, they might get sort of, depending on which chunks they retrieved, they might end up with a different block, and then they would disagree on the contents of the block. So what AVID-M does is it says, instead of trying to actually guarantee this correctness of the encoding during the dispersal process, you can defer it also to when when the nodes retrieve the block. Don't actually do it in that critical path of the dispersal. And let me describe kind of the reason you could do this. So in AVID-M, the node that is dispersing the block constructs a Merkle tree out of those chunks, and it includes a Merkle root for the set of encoded chunks with every chunk that it sends to the nodes. So now every node has an encoded chunk and a Merkle root, and a proof, of course, that this chunk belongs, to that set. So when nodes go to retrieve the block, they will collect enough chunks. They'll run the decoding like any other VID protocol. And then now they do this check. They actually check that the Merkle root that was used at time of dispersal corresponds to a consistently encoded set of chunks. And the way they do that is they basically redo the encoding. They get the encoded chunks, they construct the Merkle root, and they check, is this actually the same as the Merkle root that was committed when the dispersal happened? If this is true, if this is correct, then they know that actually that Merkle root corresponds to a consistent set of chunks. So every other node that goes and retrieves any subset of the large enough subset of the chunks and does the decoding will arrive at the same answer. And if they actually find that the Merkle root doesn't match what was committed, they know that this was an incorrectly encoded block, and they can just ignore it. The key is that everyone will actually come to the same conclusion, regardless of which set of chunks they decode because if any one of them actually found this to match, as we said, then that node actually did the encoding correctly. So the Merkle root would have committed a consistent set of chunks. Okay, so let me kind of summarize the basic idea here. So we replaced broadcast with this VID operation, and it only needs to transfer a small amount of data before nodes can actually proceed to agreement, and then eventually proceed to essentially move on to the next epoch. And then asynchronously, any block that has already been agreed upon, the nodes can go ahead and download it at their own pace in sort of parallel concurrently with running these epochs of VID agreement. So that's the basic idea. So we applied this to Honeybadger, which is an asynchronous leaderless BFT protocol. We built a system in Go. It's about 8,000, I think, lines of Go. And we've evaluated in a bunch of different sort of settings in a controlled test bed where we induced synthetic bandwidth and delay variations across the nodes, and also over in AWS and in this lower cost kind of cloud provider across different regions. And as Alexander said earlier, this cost a ton of money to just get these plots, but it is what it is. So I'm going to show you just these AWS results. So let me show you some sort of traces that give some intuition about the operation of Honeybadger versus this improved protocol that we call DispersedLedger. So this is a trace of the progress at every node on the AWS testbed in Honeybadger. So every line corresponds to the number of bytes confirmed at any point in time using Honeybadger. There's 16 of them here. Notice that they're all kind of very close to each other. So this is because in Honeybadger, you have to wait for the 2/3 slowest node to download the block before proceeding in that epoch. So they all kind of almost make progress, at the same speed. Here's the same thing with DispersedLedger. So now you have these solid lines. And notice that all the nodes in DispersedLedger actually make more progress than every node in Honeybadger. And that they're not all sort of closely clustered together anymore. Different nodes are kind of making progress at different speeds. So what this actually tells you is that in this real world testbed, there is no such thing as a node that is consistently the slowest node in the system at all times. If there was, then you would have had one of these solid lines that has to kind of be at the same speed as the baseline scheme, right? But if I actually sort of focus on the slowest DispersedLedger node, you can actually see that it starts out slow, but eventually does recover, like a minute into this experiment when presumably its bandwidth improved. So this is an example of real world kind of network bandwidth variability. So this is the overall throughput that you get at these different nodes. Roughly, we get about a 2x sort of throughput improvement over Honeybadger. We can also look at latency. So this is the confirmation latency. Again, one line for each node. These are with Honeybadger. So here we're increasing the load on the system in terms of number of transactions that are generated, and then we're measuring, this confirmation latency. So this is for Honeybadger, and again, the solid lines are for the 16 DispersedLedger nodes. Let me show you one of these nodes. So this is, say, this node in Ohio. And you can see that with DispersedLedger, we can go up to higher levels of load. We saw that the system has more throughput. But even sort of when we're in the stability regime of Honeybadger, we get much more consistently low latency. And one of the reasons for this, the main kind of reason for this, is that, again, as I mentioned, in Honeybadger, you have to download the entire block. So the duration of an epoch is kind of proportional to the block size. So as you increase the load in the system, the blocks become larger, and those durations of the epochs increase, and that's why you get this is about a 74% higher latency even when things are stable, and it's a lot more variable. In our sort of system, the duration of any particular epoch doesn't depend on the block size at all, and it remains consistently low. So faster nodes like this one, which can actually go up to higher bandwidths, are not affected at all at the lower levels of load. Here's another node. This one is in Mumbai. It's a slower node, so you can see, it can't reach the same levels of throughput, but again, it has consistently kind of low latency before it gets to the saturation point. Okay, so let me summarize there, and I think I'm running out of time. So I talked about this kind of key idea of decoupling data availability from the data delivery. This is actually quite sort of similar, I think, in concept to an earlier talk that we heard on. What was the name of the system? Little Shark, yes. But I think but sort of the key is that we are sort of showing that you could, by using this VID primitive, you can essentially make progress without any node having downloaded, the entire contents of the block. And I described this VID protocol that's kind of has linear communication, overhead, and showed you results of the DispersedLedger protocol that in real sort of test beds achieves higher throughput and better latency than previous schemes. And I'll stop there. Thank you.